So welcome back. So we are going to continue from where we left off in our last discussion here on Routh-Hurwitz criteria and especially Routh table. Right? We are going to talk about conditional stability. And as usual, during the discussion, if you encounter any issue or if you um, find out that you have a question, then please feel free to ask. All right. So in the last one, we discussed the Routh-Hurwitz criteria for analyzing the stability of continuous time, linear time invariant systems. And there we figured out a way to describe the absolute stability of a system by not actually calculating the exact pole locations of the system, but instead calculating relatively how many poles lie on the left half plane, how many poles lie on the right half plane, and how many on the j omega axis, depending on that particular scenario. We figured that out, right? And with that discovery, with that analysis, we kind of figured out a solid way of analyzing the stability of linear time invariant systems, continuous time LTI systems, right? So we figured that out. So we're going to extend that. Now, instead of saying absolutely whether a system is stable or not, here we're going to not talk about relative stability properly, exactly. So there is another term called relative stability, and we said that we are going to discuss that later on. Relative stability would, while discussing relative stability, we shall discuss, we shall figure out a way of describing the stability in a quantitative manner, describing how much stable a system is. Okay, so we would be able to put a number behind the term stability, right? Not just we won't be just able to say that this system is stable, this system is unstable, these two systems are stable, but instead we would be able to assign certain numbers representing how much stable or how much unstable a certain system is, right? So that kind of discussion will be done later on, okay, after we gather some more knowledge about this. But today we are going to talk about something called conditional stability. We are going to figure out, we're going to see that we might encounter systems that are stable under a certain condition and that are unstable under a certain condition. So we're going to figure those out. We are going to figure out certain the conditions under which a system is stable, under which the systems are unstable. Now again, whatever we are going to study in this one, in this class in particular, will be extended further later on a class discussing root locus, rather on classes discussing root locus. But that's again a later topic. All right. All right. So with that said, let's continue with our discussion today, and let's think about something very interesting, useful, right? So we know that the basic structure of a feedback control system kind of looks like this. So you have a transfer function lying here. Okay, all right. That's often called GS. Okay, and again, this would be something like the, let's rather instead just say, that you have a controller, right? So you already have done the very first class on this, I hope. So this is the controller, and then you have the plant or the system, right? So this is again often the controller, this is often the system, and this again leads to this is what goes back. And again, this is the controlled output, you already know that already, controlled variable or controlled output, whatever. This is called the reference. Okay, this is often denoted by R. Let's see. All right, and then again this signal is fed back to certain sensors and transducers, and often this is denoted as H. Transfer function is denoted as H. This is called the feedback transfer function. So essentially you measure the controlled variable by means of certain measuring elements and feed the resultant back to the input by means of a comparator, right? And this signal is called the actuating error signal, often denoted by E. This signal is called the manipulator variable, and this signal is called the controlled output, controlled variable or controlled output. So you are familiar with the nomenclature, right? And this is often called the feedback signal F, or sometimes written as B. That kind of structure is quite familiar to you, right? Now, conditional stability under this scenario, under this kind of so again, this is a very simple example of a closed loop system. Simple example of a this is what we call a very simple example of a closed loop controlled system, right? So this entire system is a controlled system because we have a controller, we have a system that is being controlled by the controller, and again we have a mechanism through which the controller knows exactly how far away the control variable is from the reference. So the control variable is what we want and the reference is what we have currently. So control reference variable is what we want and control variable is what we have. Again, these are the feedback system. All right. So this is a simple example of a closed loop control system. That's fine, understandable, quite, I think, right? Now here, try to understand that the stability of this entire system. When we talk about the stability of the system, we probably are talking about the stability of the closed loop system. So you often, instead of talking about the stability of a single system, we often talk about the stability of the closed loop system. Okay, so here in this particular one today, we are going to mostly talk about stability of closed loop systems, because we are going to see that we might somehow put a controller in a system that makes the system unstable. We might put a certain feedback element in the system that would make the system unstable. Okay, even though the system itself might not be unstable, but we might put a certain controller in the system that might result into instability for the system. Okay? So let's start with a very simple example, and from there we shall proceed. Right? Again, the tool that we are going to use is the Routh table and the Routh-Hurwitz stability criteria. Right? So let's start with this diagram, very simple diagram that we already wrote here. Now imagine something like this. We have a system that kind of whose block diagram kind of looks like this. And again, during the discussion, if you find that something is difficult for you to understand, I'll just raise the question. That's your controller block. Okay, I don't yet exactly know what controller I am putting here. Okay, that's your plant block. Okay, fine. All right, so let's say for this scenario, let's say the plant has a transfer function of, say, 1 divided by s plus 1, s plus 2, s plus 3. And just as an example, this is a very simple example that I'm considering here. But I would I would rather suggest that you learn this example by heart. Okay, kind of memorize this particular example, because this this particular example, a transfer function with 1 by which looks like 1 by s plus 1, s plus 2, s plus 3. This transfer function will be uh, referenced back quite a lot later on. Okay, this exact reference will be brought back when we study root locus, when we study Nyquist theorem, and all those things. I shall bring this example back again and again. So I would rather suggest you you kind of remember what's happening currently. This would be an example which you would probably would want to remember. Okay, not just understand but also remember. Okay, and we are in particular we are here in this example. We are considering unity negative feedback, which we already have a negative feedback. And in this one, we are going to consider unity negative feedbacks, which essentially means, okay, that the transfer function hs, that the feedback system has a transfer function of 1. So essentially, whatever signal appears as the controlled variable, so this is the controlled variable, that is actually fed back to the original comparator, right? So again, there is no essentially there is just a single, so this essentially would be just a line connecting these. So we call this a unity feedback system. So again, unity feedback is a kind of idealized idea, but you understand what I'm saying here. Now, quite often, okay. So again, just try to understand what, think about it in general. What we have here, so that's the reference input. R is the reference input, right? So this is kind of what we want. And again, we discussed this in the very first class here. Okay, and C is what we currently have, right? And we are comparing it. Like for example, for a vehicle, what we have here is kind of what we want here is, for example, for the vehicle to go at a certain speed. And currently, this C denotes the current speed of the vehicle. And this difference would determine whether I would want the vehicle to accelerate or decelerate, right? Something like that, right? So if I want my vehicle to go at 80 kilometers per hour, so if R is 80, and if currently the vehicle is going at 60 kilometers per hour, so C is 60, then I would probably want to accelerate, because the difference, so this R minus C is positive, so I want the vehicle to accelerate, right? But often what would happen is, if I want the vehicle to accelerate faster, what would I do? Okay, if I want the vehicle to accelerate faster, I would press on the accelerator pedal harder, right? I don't understand, something like this. Or something like this, maybe I want the vehicle to go at 40 kilometers per hour, but currently the vehicle is going at 80 kilometers per hour. I see that the difference is negative, so I would want the vehicle to decelerate. But while in our first class, I did not say anything about how much time I am ready to give the system to decelerate or accelerate, right? So this is my desired value for the output. So this is my desired value of the output, right? So reference input is always the desired value of the output, right? I want my output, or I want my vehicle to go at 40 kilometers per hour. So that's my desired output, right? So that is what I'm putting in as the reference input here. But again, I see the difference to be negative, so I would want my vehicle to decelerate. But how fast do I want my vehicle to reach this speed? From this to this, how fast do I want my vehicle to reach this speed would determine how hard I'm going to press on the brakes, right? How hard I'm going to press on the brakes. And of course, I would release the accelerator pedal, and how hard I'm going to press on the brakes and the clutch, right? Something like that, okay? Maybe if it's the other way around, so if this is currently 80, so I want it to go at 80 kilometers per hour, but I am currently at, say for example, 40 kilometers per hour, so the vehicle is traveling at 40 kilometers per hour currently. So how fast I want the vehicle to accelerate and reach this particular speed, so this is what I desire, so this is the desired speed. How fast I want the vehicle to reach this speed will determine how hard I would press on the accelerator, right? So kind of here the controller is essentially a gain here. The controller's transfer function could be thought like something like, say for example, just a gain. So instead of just giving the difference between the reference and the um, controlled variable, we are multiplying the difference, okay, with a certain number which is probably greater than 1 and feeding that to the input. So this is a very simple controller. Okay, this is a very simple controller. Sometimes, okay, I'm telling you a story that many of you might probably be able to relate to that. When I was a student, maybe I was sleeping late, so I was going late for my school or maybe my college. Okay, and my mother would suddenly come and suddenly say, okay, okay, get up from bed, it's already 11 o'clock, maybe 10 o'clock. And I would get a shock that, okay, I'm going to miss college today, or maybe miss school today. Okay, I would wake up, okay, rub my eyes, and then see that it's only 8 o'clock in the wall clock, essentially. But my mother woke me up saying that it was like 10 o'clock or something like that. Something like that might have happened to you as well, right? It surely happened to me quite a lot. Something like that does happen, right? Why? So in that case, my mother was acting as a controller that kind of looks like this. So I was late, kind of, but how much late I was, okay, was kind of exaggerated. Okay, it was kind of exaggerated. So that was an exaggeration. So this is kind of exaggerating how much difference it has, right? So currently I want my vehicle to go at 80 kilometers per hour. It's going at 40 kilometers per hour. So the difference should be 40, but the system is now going to see, so the difference is 40, right? But the system is now going to see 80. Okay, so kind of you are saying that you have to push even harder, something like that. Okay, that kind of information you are getting, right? So power of exaggeration here in this case, right? So this is a very simple controller configuration, and this kind of controller, okay, again, this is a controller, right? We said this kind of controller is known as a proportional controller. And this is again the system, and we have unity negative feedback. Okay, unity feedback has a very useful short form. It's called UFB. It's so common. We encounter unity feedback systems so commonly that it has a short form. It's called UFB. Okay, unity feedback. FB stands for feedback here. And again, proportional controls are again so common. It's sometimes just called P controller. Okay, it's sometimes just called P controller, right? And here, this is often not just some fixed value, or rather some variable value denoted by K. Denoted by K. So this is a very simple configuration. Very simple configuration. Okay. So what it does, it essentially takes the actuating error signal, multiplies it with certain value. Again, the kid is shouting. Okay. So it takes the actuating error signal, and here in this particular one, this is not actuating error, just the error signal, and multiplies it with a certain value, certain scalar quantity, and feeds it as the manipulated variable, right? So this is the manipulated variable. Manipulated variable is Ke here. Okay, all right. So that's something it does. So it increases or decreases the actuating error signal proportionally. So it's called a proportional controller. But in the same vein, we might want to differentiate the error signal and feed it to the system. We might want to integrate the error signal and feed it to the system depending on the situation, right? And if I have a controller that does some proportional increment to the error signal along with some derivative and some integration on the error signal, we essentially have a controller which is called the proportional integral derivative controller, often known as, in short, PID. So this is again the very first baby step towards having a PID controller. Again, we are going to discuss controllers in detail later on. All right. And just as a reminder, after the end of the semester, we shall have some additional classes on this subject. Okay, things that are not supposed to be in your, that are not there in your course per se, but things that you would probably want to learn in case you are interested about this topic. So those classes won't be mandatory, but later on we are going to discuss these things a bit further. Okay, after the end of the semester anyway. All right, so we shall see quite a few practical examples then. But again, if you are not interested about the subject, those things won't interest you either. All right. All right, so that's something we have here. Okay, but now try to understand that these two blocks are cascaded, right? These two blocks are essentially in cascade, right? So now for all intents and purposes, I can say that this is just a single block. Okay, and this system kind of looks like this. So this entire thing kind of looks like this. So we have this comparator, and this entire thing kind of looks like a single block that has a transfer function of k divided by s plus 1, s plus 2, s plus 3. Okay, that was the output. Since we have just done a very small block diagram reduction here, right? And this is the minus. All right. And again, whenever you are drawing block diagrams, make sure, I make absolutely sure that you put the arrows. If any of the arrow in a block diagram or a signal flow graph is missing, it does not make any sense anymore. Okay. Sometimes we can infer the direction of the arrows, sometimes, but if we cannot somehow infer the direction of the arrow, okay, then it becomes complete nonsense. So again, this is R, this is C. All right. So now this is a very simple, and now here, while discussing the stability of the entire system, now try to understand. We now have a parameter in our system. What parameter? We now have a parameter k in our system. K is a variable quantity. For our intents and purposes, k is a positive variable, because of course when I want the speed to increase, I want a positive difference, and when I want the speed to decrease, I want a negative difference. So this number cannot be negative in that obviously this number cannot be negative. K is obviously a positive quantity, right? K is obviously a positive quantity, but how much, right? How much can I exaggerate here? So this is kind of, we often we actually have still a very what should I say, he is currently an emeritus professor. Okay, and we were quite lucky enough to get him as our teacher. His name is Professor Tapun Ghoshal, and he's one of the most renowned people in India on control systems. So we were lucky enough to have him as our teacher. So actually, while teaching this kind of things, so he said that this is acting as an exaggeration. So this is this controller, proportional controller, is exaggerating the error signal, right? But just like in real life, you can exaggerate to a certain level, up to a certain level. If you go beyond that, what happens is everything falls apart. Your friends will become your enemies if you exaggerate way beyond what you should have done, right? So that is exactly what we are going to see here. We can put a proportional controller to exaggerate the error signal, right? But we can only go up to a certain value for k. If I go beyond a certain value for k, we will see that it would essentially make the entire system unstable, make the entire closed loop system unstable. Something exactly pretty similar to what happens in our real life. Okay. Okay. You can lie, but at a certain point, your lies essentially becomes your enemy in your life. Okay, something like that. Okay, all right. So we have a system like this. So essentially, for the most part, this is something we can call GS. Okay, for all intents and purposes, we can call this transfer function GS, and we can say, okay, we have a system, we have a closed loop system. We can describe this as something like this: a closed loop system with GS equal to K by S plus 1, S plus 2, S plus 3, and HS is equal to 1. Again, if I don't say anything, it is assumed that we are talking about unity negative feedback, right? So if we are talking about negative feedback, right? So these are the things, just keep in mind, standard what should I say, standard conventions. Yes, someone is saying, why would anyone want to exaggerate the error signal? And you have answered your question. You're saying, is it to reach the desired speed faster, desired result faster? Yes, absolutely right. So proportional controllers make the response faster. Okay, make sure that the response is faster. Absolutely. Okay, but it comes with a what should I say, it comes with its own perks, right? But almost certainly the purpose of a proportional controller is to make sure that the desired output, which is the controlled variable, reaches its desired value, okay, faster. So if you want to make the response faster for a particular system, you might want to put a proportional controller blatantly. Okay, you might want to put a proportional controller. Again, the whole purpose of a proportional controller is like to make sure that the response is reached faster, right? And again, this proportional controller is amplifying the signal here. So this E is becoming KE. Sometimes this proportional controller is also called a linear amplifier. So it has so many names. Okay, it is just a linear amplifier which is amplifying a certain signal. Think about electrical engineering, right? So this is often a simple thing like an amplifier, right? But yes, its purpose would be to make sure that the response is faster. All right, but you can only make it so fast before actually breaking the entire stability of the system. Well, almost certainly connecting a proportional controller would make the system faster, but we're going to analyze these things later on through certain analytical tools. Okay, why does adding a proportional controller makes the response faster? We're going to answer those questions later on analytically, right? Not by just giving you examples, particular examples, but by giving you the general idea behind all this, right? Anyway, so this kind of idea is fine, right? But there are a few, what should I say, there are a few standard what should I say, untold, rather, we do not really mention these kind of things, but these are assumed throughout. Okay, if you are talking to a control system engineer, or if you are a control system engineer, you already assume these things. So what are the assumptions we often have? If we did not say anything about whether the feedback was negative or positive, assume negative. So if I say a closed loop system with a forward path transfer, so this is again, this has a name like forward path transfer function. Forward path transfer function. So if I say we have a closed loop system with this forward path transfer function and this feedback transfer function, but I do not say whether it's a positive feedback system or a negative feedback system, always assume negative feedback system because that's the default. Okay, if it's a negative feedback system, we do not bother to mention. Okay, and if we do not even mention anything about the feedback, for a closed loop system, okay, maybe we are saying a closed loop system with a forward path transfer function this, and if I didn't even mention anything, so it might so happen that I would say something like a closed loop system with this forward path transfer function, and if I just skip the rest, you would have to assume that I am talking about a negative feedback system whose feedback transfer function is 1. So we are talking about unity negative feedback system. Okay, so if we do not mention anything about the feedback for a closed loop system, assume unity negative feedback. Assume that, right? Because this is also default. So if I say it's a closed loop system, which means it has a feedback, but I don't mention anything about the feedback, then assume unity negative feedback. Okay, but again, if I tell you that it's a closed loop system and I give you the transfer function, feedback transfer function as well, but I don't mention anything about whether the feedback is negative or positive, assume negative feedback. So essentially, if we have a positive feedback system, I would specifically tell you that it's a positive feedback system. Okay, and also the transfer function for the feedback transfer function, right? You understand, these are the kind of untold defaults in control system realm, right? Just keep that in mind. Okay, also for your exams. Okay, if I just give you the forward path transfer function and say it's a closed loop system, you have to assume that we are talking about a unity negative feedback system, right? All right, so we have this transfer function, right? We have this transfer function, right? And negative feedback, of course, and this feedback transfer function. That's one, right? So what is the closed loop transfer function? Closed loop transfer function would be the transfer function between CS and RS. Okay, output divided by input. So that's output. This CS is the output and RS is the input. So closed loop transfer function is between CS and RS. Okay, ratio of CS and RS when all the initial conditions are 0. So that's going to be GS divided by 1 plus GS HS, right? That's the closed loop transfer function, right? That's understood, quite easily understood, right? So let's construct the closed loop transfer function in this one particular. Okay, so what was our GS? GS was K divided by S plus 1, S plus 2, S plus 3, and this is now going to be 1 divided by K divided by S plus 1, S plus 2, S plus 3 times 1, because H is 1, right? Now if I simplify this, of course this becomes K divided by S plus 1, S plus 2, S plus 3 plus K, right? So now for the closed loop system, so this is the closed loop transfer function, right? We often denote this as TS. So this is the closed loop transfer function, right? Right? This is the closed loop transfer function. Now, if I think about it, what is the characteristic equation of this, characteristic polynomial of this? What is the characteristic polynomial? So that's the denominator in the closed loop transfer function. So we are saying characteristic polynomial is this one. This is S plus 1, S plus 2, S plus 3 plus K. So that's your characteristic polynomial, okay, which is the denominator is polynomial. Okay, so this will determine the poles of the closed loop systems, aka the closed loop poles, right? this would determine the closed loop poles. If I equate it to 0, the solution of this equation would determine the closed loop poles, and the closed loop poles would determine the stability of the system. So now if I ask you to think about the stability of the closed loop system, so we can assess the stability of the closed loop system by looking at the characteristic polynomial of the closed loop system. So this is the characteristic polynomial of the closed loop system, right? Of the closed loop system. Right? That's the characteristic polynomial of the closed loop system. That's understood, I think, right? So this is the closed loop transfer function. That's the characteristic polynomial of the closed loop. All right. So what polynomial do I have? I have this polynomial, right? So I have s plus 1, s plus 2, s plus 3 plus k, and which can be expanded to something like let's do the multiplication, right? That's gonna be s cubed plus 11 s square plus 6s plus 6 plus k. All right, so that's the polynomial, right? Now we can use, now let me understand, so this is the polynomial, and again this is the constant term in the polynomial. Now the roots of this polynomial, okay, roots essentially means I equate it to 0 and solve for it, right? The roots of this polynomial are the poles of the closed loop system, right? Okay, so essentially if I think about this a polynomial, then it determines the stability of the system, stability of the closed loop system, right? And how do we discuss the stability? Do we really want to solve this polynomial? No, but instead I'm going to write down the route table. But try to understand something very crucial here, something very important here, is that the stability would probably depend on the particular value of k, because try to understand, if the value of k might be something for which this polynomial violates the sufficient criteria for stability in the route table. Okay, now we can right off the bat we can verify that this is actually satisfying, this polynomial is in particular is satisfying the necessary criteria for stability, right? So this is the polynomial, so s cube plus 11 s square. I think I wrote it wrong, right? Sorry, I did the calculation wrong, really sorry. So with s square I would have 6 s square. Somehow none of you actually pointed that out. Okay, 6 s square plus 11s plus k plus 6. So that's the polynomial, right? And depending on particular, so this is satisfying the necessary criteria, right? Because all the coefficients are present, so it's a third order polynomial and all the 4 coefficients are present. So this is 1, 6, 11, k plus 6, and all of them are positive, they have the same sign because k is greater than 0, right? So since k is greater than 0, we already assumed that k is greater than 0, it satisfies the necessary criteria, right? It satisfies the necessary criterion, so that's fine, right? Now construct the route table. We could have solved this and we would do it in a better way, much better way later on, but let's for the moment construct the route table. So s cube, we have s square, s to the power 1, and let's with some gaps. S cube and S squared are fine. Then S to the power 1 and S to the power 0. All right. So what do I have? What are the factors here? So we have 1 here. We have k plus 6 here. Sorry, 1 here and 11 here, right? 1, 1, 11, 6 and k plus 6. Remember, k plus 6 is the constant term. You wouldn't have this as separate terms, right? Because these are the both coefficients of S to the power 0, right? This is the constant terms, right? So what about, so let's put certain space here. That's fine, right? All right. So what about this term here? Again, this term can be calculated by this product minus this product and divide by this product, this pivot value, right? So with that said, it's going to be 6 times 11, so that's 66. That's going to be 66 minus 1 times k plus 6, so that's going to be k plus 6 divided by 6. All right. Let's now simplify this. So that was 66 minus k plus 6 divided by 6, right? So 66 minus k minus 6, that's going to be 60 minus k, right? So instead of writing all these, let's write 60 minus k divided by 6. So 60 minus k divided by 6, that's fine. And of course, this is you have a trailing 0 here, of course. But again, you can skip writing this, or you can just write this if you want, all right? And the next term would be again this. Next term would be this times this, whatever that is, minus this times this, minus this times this, that's 0. So we essentially have this times this, right? Minus 0. So essentially the product of these two terms. And then we have to divide by this. We have to divide by this, right? So this multiplied by this, okay? Subtract 6 times 0. So essentially we are left with this product, and we have to divide by 60 minus k by 6. So essentially we're going to leave, we are going to be left with k plus 6, right? If we do the calculation, that's going to be k plus 6. All right. Now we don't have particular fixed constants here. Instead, we now have a parametric, a variable value, right? This k was a parameter, right? We had a transfer function with a parameter. Now we have a parametric solution here. Now for stability, right? For stability, there shouldn't be any changes in sign in the first column of the route table, right? Right? We are saying for stability, all these terms should have the same sign, right? There shouldn't be no sign changes. So this is a positive quantity, this 1 is a positive quantity, this 6 is a positive quantity, this 6 plus k is also a positive quantity because k is positive, we already assumed that. But this has to be positive. This will have to be positive, right? This will have to be positive. And if it is positive, then there won't be any sign changes, right? Positive to positive, positive to positive, positive to positive. There won't be any sign changes. So now we have to ensure that this particular term is also positive. So this is the criteria. For stability, all the poles must be lying on the left half plane, and for that 60 minus k divided by 6 must be greater than 0. This term has to be positive. And I think that's quite obvious, right? And with that, we can now further proceed with this, multiply both sides with 6. And since 6 is a positive quantity, this becomes the direction of this doesn't change. So it becomes 60 minus k greater than 0. And if you do the simplification, it essentially means 60 is less, k is less than 60. Of course, if k is less than 60, 60 minus k becomes greater than 0. How is this one k plus? Someone is saying, how is this one k plus 6? How is this one k plus 6? Okay, this is k plus 6 by simply multiply these two and subtract these two and divide by this. Okay, so this term would be 60 minus k by 6 times k plus 6 minus 6 times 0. Okay, divide by 60 minus k by 6. Do the calculation. you're going to get k plus 6, right? And of course k plus 6 is assumed to be greater than 0 because k is greater than 0 already. If k is greater than 0, k plus 6 is greater than 0, right? Alright. So you can happily put a trailing 0 here. Also, you can happily put a trailing 0 here. I'm doing it, but in this particular case to make you understand something here. Right. So for stability, we have a condition. We already have. Oh, sorry, it's not going to be 6, right? It's going to be 6. For stability, we already now have a condition. If k reaches 60 or goes beyond 60, then the system becomes unstable, not stable. So we can ensure absolute stability as long as k is less than 60, right? Right. So also we previously assumed that k was greater than 0. So combining those two conditions, also since the necessary criterion requires k greater than 0. Of course, the necessary criteria would be violated if k is less than 0, right? K greater than, also rather say, also since we set k greater than 0, k to be positive, alright? So we're just going to say for stability, therefore the closed loop system, and since this term closed loop is used so often, it also has a short form. It's called CL. Okay, since the CL system, therefore the closed loop system would be stable. If k is less than 60 but greater than 0. Under that condition. All right. Now let's bring this route table back. Here. Copy, pasta. Right. Nice. Now question is what if what if k is greater than 60? What if k is greater than 60? Right? What if k is greater than 60? If k is greater than 60, then this becomes negative, right? This becomes a negative quantity. If k is greater than 60, then this becomes a negative quantity. Then you would have no sign changes here, but you would have one sign change here from positive to negative, and then another sign change here from negative to positive, right? If k is greater than 60, this is positive, this is positive, this is positive, right? This is positive, but this is going to be negative, right? That's understood. All right. So with that knowledge, I can say if k is greater than 60, then I see two sign changes, one from this to this, another from this to this, right? From 6 to this, and from this to k plus 6. We have two sign changes. So that's if k is greater than 60, then so I think so if k is greater than 60, we see two sign changes on the first column of the route table. Thus, there would be two poles on the right half plane. So these are the two poles responsible for the instability, and the remaining one pole, of course it's a third order system, so there will be three poles. Two are on the right half plane, so the remaining one pole would be on the left half plane. So we are writing, therefore, if k is greater than 60, the CL system, which is the closed loop system, would be unstable. And again, we are saying all these things without actually calculating the poles, right? Without actually calculating the poles, we can say all these things about the system. Sorry, k greater than 60. What did I write? If k greater than 60, the closed loop system would be unstable, right? So we can say something like this. Now, the most interesting question comes last, right? The question is, what about k equal to 60, right? And now you might, some of you might be very clever and might be able to guess about it already, right? So if k is less than 60, the system is stable. If k is greater than 60, the system is unstable. Then what about k equal to 60, right? What about k equal to 60? And for that, I would copy paste it once more. So if k is equal to 60, so if I put k equal to 60, putting k equal to 60. If I put k equal to 60, what does this one become? This one essentially becomes 66. This one becomes 0, right? K equal to 60, that's 0, right? And this one becomes 66. So I have no problem with this, but I have a problem with this because this is now 0, right? So we have an entire row of zeros. So this is an entire row of zeros. Entire row of zeros. And when we encounter an entire row of zeros in the route table, that's indicative of difficulty 2, right? So we encounter a difficulty, we would encounter a difficulty 2 conditionally if I put k equal to 60, right? So we have to do something about it. We have to treat it the way we did treat our difficulty 2 situation. So we are going to construct the auxiliary polynomial, right? So what is going to be the auxiliary polynomial? Auxiliary polynomial is going to be constructed through the previous row, and here it's in a square row. So the auxiliary polynomial is going to be 6s square plus 66s. 6s square plus 66s. But you already know that I have to do a factoring here, right? So we have to do a factoring here. Since this is 6 and this is 66, we have to do a factoring here. So essentially we have to factor out 6 here. So that becomes 1 and this becomes 11, right? All right. But this again becomes stays a 0, right? It stays 0, but slightly differently. So this becomes actually 11. Sorry, this becomes so it becomes, wait a second, 11 minus k minus 6. Yeah, sorry. So this essentially becomes just a simple. Let's write it down. So better, and this becomes 11, right? All right. Let's put the particular values here, right? So what is the auxiliary polynomial here? That's gonna be s square plus 11, right? Auxiliary polynomial. So what do I do? How do I construct the new how do I construct the new s square row? Sorry, new s to the power 1 row. So that's going to be the new s to the power 1 row. Okay. And how do I construct that? We construct that simply by differentiating this. So if I differentiate this, you get 2s plus 0, right? So that's going to be this, the derivative of this, right? So we differentiate this and we put the coefficients there. So we would have 2 and 0 here. So this is after the modification. So the entire row of 0. So we have a difficulty, we add a difficulty 2, the second type difficulty here, and then we rectified that by constructing a new row out of it, right? Through the auxiliary polynomial. And now that's fine, right? So how many sign changes do I see now? Is there any sign change? No. Is there any sign change? No. And this is again discarded. So this has been discarded. And is there any sign change? Once again, no. So it actually goes from positive to positive to positive, right? There are no sign changes, right? So no sign changes. But we encountered difficulty 2, and difficulty 2 does not say necessarily that the system would be unstable, but it says the system would be not stable, right? There's a reason for that. So we did not see any sign changes, so right? So in this particular case, so we are saying thus we see that setting k equal to 60 does not cause any sign changes on the first column of the South table. Thus, the system will not be unstable. Thus, the system will not be unstable, but it is not stable either, because we already figured out the condition for stability, and the condition for stability was that k was strictly less than 60, not equal to 60, right? So of course this is the auxiliary polynomial, and auxiliary polynomial is a factor of the original polynomial. Yes, the factorization theorem says, actually this is entirely built upon the factorization theorem, and the factorization theorem says that you have to factor this out, okay? But if you don't, just someone of you asked, one of you asked, what if I don't do this without factorizing it? I'm just going to show you later on, just moments after actually establishing the whole thing, okay? So this is the factor. So now under this condition we encountered an auxiliary polynomial, right? So the auxiliary polynomial was s square plus 11. I will remember your question, and after completing this I'm going to tell you your answer, right? So auxiliary polynomial is this. So which indicates, what does it mean? It implies that the original polynomial, which was s cube plus 6s square plus 11s plus k plus 60, which is now 66 in this one, right? Because k is 60, right? So that's going to be 66 is factorizable this way. It is s square plus 11 and then something, right? This is going to be a factor of the whole thing. If k is 66, k is 60, then this is simply factorizable this way. We figured out this factor. So this is auxiliary polynomial, and auxiliary polynomial has to be a factor of this, right? And of course, if I just can figure this out, there's going to be s plus 6. Okay, that's again very simply can be understood, right? Okay, we figured this out manually, right? So again, so solving for the exact pole locations, if I solve for the exact pole locations, so that's going to be solving for this equation. So s cube plus 6s square plus 11s plus 66 equal to 0. Solving this would give us the exact closed loop poles, right? The closed loop pole. But this is again equivalent to s square plus 11 times some first order term, which is s plus 6, but I don't bother about that right now. But this is again a particular solution here. So this is again giving me two roots, right? So this implies that there are two roots, s square plus 11, for which the s square plus 11 equal to 0. So these are at s equal to plus minus j root 11. And other one is at minus 6, right? So this is s plus 6, which I can figure this out. And this is going to be, again, this is immaterial in this one, in this particular case. And the other one would be s plus 6 equal to 0, which indicates s equal to minus 6. So if I do a pole zero map here, if I draw a pole zero map here, again, this is the real part of s, and this is the imaginary part of s. If I do a pole zero map, I would see that one of the poles are here, one of the poles are here, another is here. So that's at minus 6, and this is plus j root 11, and that's minus j root 11. So we have a marginally stable system. So with this entire concept, we say the system will not be unstable, okay. So we are saying the ultimate conclusion is, therefore, when k is equal to 60, exactly is equal to 60, there would be one pole on the left half plane and two poles on the j omega axis. Thus the system would be, I should really say, two complex conjugate pole pairs on the j omega axis, okay, one complex conjugate pole pair on the j omega axis, but you get the point. Thus the system would be marginally stable. Just to recapitulate what we just figured out about the entire thing, so let's call this back here. So this was our system, right? So for this system, we figured out that the closed loop system would be so for this system, we figured out that the closed loop system would be stable if k is strictly less than 60, and of course greater than 60. So let's write greater than 0. So let's write that out. Unstable if k is greater than 60. Marginally stable if k is equal to 60. See, we figured these out without actually calculating the roots, right? We did calculate the exact values of the roots at a certain point for k equal to 60, but other than that, we didn't calculate any of these. So we figured this out. And for instability, we also figured out that there will be two poles on the right half plane and one will be on the left half plane. Now ask any question that you might have. Okay, you already had a question. I was just somehow about to forget that. So just to say that you didn't cancel this out. Say you are saying this is 6 and this is 66, fine. So your auxiliary polynomial is going to be 6s square plus 66, right? That you understand now. So if this, so this is again rough work, okay? I'm going to delete that. So your auxiliary polynomial would be 6s square plus 66. But this is not going to be a factor per se. But the thing is, this is again true in a sense. So 6x square plus 66. So accordingly, you would write 12 and 0 here. No problem. So your conclusion would be the same, that if you write 12 and 0 here, your conclusion would be the same, right? But now, what about the auxiliary poles? So these are the this is the auxiliary polynomial, right? So if I equate it to 0, I get the poles on the j omega axis, right? Now if I solve for this 6s square plus 66 equal to 0, if I solve for this, I would eventually end up with s square plus 11 equal to 0, and the locations of the poles on the j omega axis will not be affected whether or not I factor out the common factor out from the route table or not. Even if I don't factor out the common factor from the route table, okay, the solution is still the same. But unfortunately, this will no longer be a factor of the original polynomial. But instead, the solutions of this, instead we will be able to say in general, the solution of this would also be the solutions of the original polynomial. Instead of saying that the original polynomial can be factorized with this, instead of saying that, we would be now able to say that the solutions of this would also be solutions of the original polynomial. Essentially, the roots of this polynomial would also be roots of the original polynomial. So essentially the same thing, right? With slight complications. So I would suggest you that you reduce the factors, all the factors. But if you don't, nothing wrong is going to happen. Nothing is going to go wrong, right? It's going to be absolutely correct. You would have the same explanation, same answer. Okay. So even if you consider this to be, even if you don't cancel it out, if you write it as 6 and 66, you would end up with 12 here, you would end up with 0 here, and subsequently here you'll end up with 66. But the explanation, yes, the particular values will change on the route table, but again on the route table you are not interested about the values. When we are talking about the route table, we are only interested about the sign changes, how many changes in sign do happen, right? So as long as that does not, as long as that fact is not affected, doesn't matter, right? So if I write 12 here, okay, if I write 0 here, if I write 66 here, the fact that there are no sign changes does not change. So it does not affect the route table in any meaningful way. The auxiliary polynomial becomes 6s square plus 66, but again solving that would give you the same solution as solving s square plus 11 equal to 0. So yes, you have the same exact locations of the roots on the geometric axis. You have the same inference that there are no sign changes. You have exactly the same inference. So yes, as long as your inference does not change, doing this in the other way does not matter. That is what I said. That is why I said taking out these factors was completely optional. And when I said that, I really meant that you didn't have to selectively take out the factors or not. It wasn't like that. So I think this was understood. If you have any query. So the proportional controller can exaggerate the error signal up to a certain point, but beyond that the whole closed loop system becomes unstable. But one very important point to note here, the system that is inside, so that's the forward path transfer function, this system does not become unstable even if k becomes thousands or whatever, right? This system itself, gs itself, does not become unstable, right? Because gs itself has fixed poles, right? gs itself has fixed poles. One of the poles is at -1, one of the poles is at -2, one of the poles is at -3. gs itself has fixed poles, but the closed loop transfer function ts does not have fixed poles. Its pole locations will vary depending on the value of k. So increasing k beyond 60 makes the closed loop system unstable. It does not affect the internal system plant here, right? It only makes the closed loop system unstable. It only makes the whole thing unstable, not the internal things, right? Got it? Right? So again, you can think about it in a very generic sense, like driving again. So you want your vehicle to go at 80 kilometers per hour. Currently you are running at 40 kilometers per hour. You see a positive difference. You have to press the accelerator harder. Now you somehow pressed it so hard that there is no way of coming back, right? You pressed it so hard that it immediately went beyond everything. That's how instability occurs here. Okay, let's take another example, a slightly more complicated example. Okay, slightly more complicated example that would help us understanding something. Let's take another example. All right, a closed loop system with, hold on, right. So now again you can understand that the transfer function internally was s plus 6 divided by s into s plus 1 into s plus 3, and proportional controller was there, right? And I'm saying closed loop system with nothing else. You have to understand it's a negative unity negative feedback. Now I'm giving you 5 minutes to come up with what happens here. Okay, condition for stability. At least figure out the condition for stability. Maybe in 2 or 3 minutes you can figure it out if you know how to do it. So construct the closed loop transfer function, figure out the characteristic polynomial, and I shall come back within 2 minutes. So alright, I don't see anybody saying anything, so let's resume here, right? Alright, so I think you understood this. We're assuming negative feedback, assuming unity negative feedback, right? So of course my closed loop transfer function Ts is going to be Gs divided by 1 plus Gs Hs. Now of course Hs is equal to 1. So if you do the calculation, it becomes k by s plus 6 divided by s into s times s plus 1 times s plus 3 plus k times s plus 6. So right, so therefore the characteristic polynomial of the closed loop system becomes, okay, someone already got an answer. Let's see whether it's correct or not. So characteristic polynomial for the closed loop system becomes s times s plus 1 times s plus 3 plus k times s plus 6, right? Of course, if I simplify it further, so it becomes s square plus 4, sorry, becomes s cube plus 4s square plus 3s plus ks plus 6, right? Sorry, ks plus 6k, right? So now we have to, I mean, bring the common factors together. Okay, so collect the terms. Let's see, s4 s cube 4s square, then it is k plus 3 times s, and we just have a constant term, that's 6k, right? I don't think we have made any mistake, right? So s square plus 4s s cube plus 4s square plus 3s, and we have ks here, so that gets added up, and we have 6k here, right? So now let's, of course, k is again k is greater than, k is positive, right? So again, since k is positive, I can see that it satisfies the necessary criteria, right? Now since k is greater than 0, okay, all right. So let's construct the route table. So we don't have any space here, so I shall bring the polynomial to the other page and continue from there. So that is what we are looking for, what we are doing here. So s cube, and then we have s square, it's a polynomial, right? So we would have s to the power 1 and s to the power 0, right? So we would have 1, we would have 1 here, and k plus 3, and we would have 4 and 6k, all right? And now we can of course figure this term out, right? We can figure this term out, and what would this term be? This term would be k plus 3 times 4, okay, minus 6k divided by 4, right? So that's going to be k times, so 4 times k plus 3 minus 6k divided by 4 because of this. And of course here I have, so again this is a 0, trailing zeros can be written, can be skipped, and this is going to be 6k. All right, so here again all the terms are positive. This is positive, right? This is a positive term, this is a positive term, this has to be a positive term, and this is a positive term since we already assumed k to be greater than 0, right? All right, some of you already got the answer, right? So now let's simplify this term, simplify this. So that's going to be 4k plus 12 minus 6k, so that's going to be 12 minus 6k, 4k plus 12 minus 6k, so 12 minus 2k divided by 4, so we would have 12 minus 2k divided by 4, or 6 minus k by 2. That is what we have after simplified calculation. All right, so of course it's positive. This is going to be positive if k is less than 16. So we already now so we already have the system would be the closed loop system would be stable if k is less than 6. We already have this, right? Nice. Okay, of course the closed loop system would be unstable if k is greater than 6, and if k is greater than 6, then we have positive to positive, positive to negative, and negative to positive. So two sign changes. So two poles on the right half plane, one pole on the left half plane. All right, and of course marginal is stable at k equal to 6, obvious. Okay, let's now think about the marginal stability condition. Let's copy this, copy and paste this. We can calculate this, right? So put k equal to 6, put k equal to 6. If I put k equal to 6, that becomes 9, that becomes 36, right? So I can now of course reduce this term, factor these out. So this becomes 1 and this becomes 9, obviously, and this becomes a 0 and this becomes a 9, right? Okay, this becomes a 0. So we have an entire row of 0. So again, difficulty 2 situation, right? That's a difficulty 2. So we have entire row of zeros. That's difficulty 2. Difficulty 2, right? So of course we are going to consider this as auxiliary polynomial. Auxiliary polynomial. Aux poly would be 1 s square plus 9. So s square plus 9. So derivative is 2s plus 0. So our newly constructed s to the power 1 row, so this is discarded. And this is the new one. Newly constructed would be 2 and 0. Of course, this has been discarded. And of course, from that, this is going to be 9. So there are no sign changes. There are no sign changes. And this is the auxiliary polynomial. Okay. So of course, the poles would be at poles on the j omega axis would satisfy s square plus 9 equal to 0. So the poles on the j omega axis would satisfy the auxiliary polynomial. So because this is going to be a factor of the whole thing, again, whole polynomial, right? So that is s equal to plus minus j p, right? So the poles would be the poles on the j omega axis would be at plus minus j3. So again, of course, thus the closed loop system would be marginally stable if k is equal to 6. So one pole on the left half plane, two poles at plus minus j3, right? Two poles on the j omega axis. So we have inferred all the three things about the system. All right, I don't think there is any confusion with this. Of course, you can figure out the rest of the poles by just doing the factorization, completing the factorization, right? So once you know the factorization, so once you know that this is a factor, you can always take out the other factor and you can precisely know where the rest of the poles are, rather at least the other pole is there. Let's solve another one. Right. So now we have let's do a fourth order one. All right. Of course, HS is equal to 1. It's a negative feedback system. Everybody understands this. Yes, someone is asking, is it going to be stable for a certain value of k less than something, unstable for greater than something, marginally stable at something? The only thing that you can rest assured is that the system will be marginally stable for certain values of k. Okay, so for marginal stability, the condition would look like k equal to something, but for the rest, I do not know. This is going to be an example for that. Marginal stability will only happen at particular values of k, not just ranges of value of k, right? But for stability and instability, these conditions might be different. Let's see this example. Okay. Of course, calculate the closed loop transfer function. Okay, Ts is going to be, if you do the calculation, Ts is going to be k times s plus 2, and this is going to be s into s plus 2 plus s plus 3. That's going to be gs by 1 plus gs, since hs is equal to 1. Just calculate this. I sincerely hope that this is going to give me trouble. Okay, that is what I'm hoping for. If it doesn't, we shall solve another problem. Right. So of course, the characteristic polynomial is this one. Characteristic polynomial of the closed loop system is this whole thing, right? So that's s times s plus 2 times s plus 3 times s plus 4 plus k times s plus 1. So let's simplify this. So that's equal to s times s cube plus nine s square. Just please do the calculation. Don't rely on me when it comes to calculation. Please do the calculation yourself, so that actually you can point out any mistake that I might have made. So this is s to the power 4 plus 9s cube plus 26s square plus 24s plus ks plus k, and of course we have to collect the like terms. So s to the power 4 plus 9s cube plus 26s square plus k plus 24 s plus k. Please affirm, please confirm that this is correct. Because I'm a supercomputer when it comes to calculation. All right, let's construct the route table. So that's gonna start from s to the power 4 and go up to s cube, s square, power 1, and s to the power 0. Okay, nice. Thank you. Thank you for confirming. So I have 126. So 126 and k on the first row. So 126 and k on the first row. So 126 and k. The next one I would have 9 and k plus 24 and 0. 9 k plus 24 and 0. Again, this is a trailing 0. I could have skipped this. Okay, and assume that there is a 0, but I'm writing this. Okay, just to make sure that you understand what's happening. Unfortunately, I'm not going to encounter a difficult situation. Am I going to? Let's see. Let's see. If I don't encounter a difficult situation, significantly more difficult than what we have, we're going to do another one. Right? Again, k is greater than 0. That's assumed, right? All right. So what about here? Okay, I have to bring out my calculator here. Of course, since I have a computer, I do have a calculator as well. Nice. All right, so 9 times 26. 9 times 26. That's 234. So this is gonna be 234 minus k plus 24 divided by 9. Okay, and all right, 9 times 26, that's 234, and 234 minus 24, that's 210. So 210 minus k by 9. Okay, that's gonna be 210 minus k by 9. What about this one? This one is becoming k times k plus 24 divided by k plus 24. So that's just k, right? That's just k. All right. All right. So if you have come up with something, okay, if you encounter anything that I have written wrong, please feel free to tell me. As I told you, I'm really good at calculating things manually. So that is why I do not rely on myself while calculating anything. Okay, I always rely on a computer program. Okay, so here, what is the term here? That's gonna be a little bit difficult to write, I think. So this is gonna be this times this minus this, and so much complicated things. Yes, I have got what I wanted. I wanted a complicated thing. I got a complicated thing. So k times 24 times 210 minus k divided by 9 minus 9k, and the whole thing must be divided by 210 minus k divided by 9. All right, that's just the first term, right? And of course the next term would be, so again I could have put a trailing 0, right? Right, this is just the first term, right? And here I have the same thing here. So if you just do the calculation, it's going to be 0, right? This one is going to be 0. All right, and this one is going to be just k, right? Okay, so these are the two terms. Now we need to verify that they are greater than 0. Or someone just jumped into the conclusion that saying k less than 210. This might not be true. This might not be true. Okay, okay, just one more thing, one important thing. We see that k is greater than 0. So again, these two are positive, right? These two are positive. This is positive, this is positive. K is greater than 0 by assumption, so this is also positive. I have to figure out the condition to make these two positive, right? I have to make sure that the condition is suitable for that. So of course k must be less than 210, something we can see right off the bat. Okay, so we are now figuring out the condition for stability. So for stability, k must be less than 210, but that's not it. By ensuring k to be less than 210, we ensure that this term is positive. Okay, but I have to also ensure that this term is positive. So let's do the calculation here. Let's do the simplification here, right? Unless we simplify this, we wouldn't know what that term actually is, right? So let's do a simplification on this. Let's try. We could have just employed Python to do this for us, but I'm not doing that. I'm not cheating here, at least. So that's going to be k plus 24 times 210 minus k. Seriously, I could have just used Python. Would have been much better for me. Okay. So we are just saying this is there. Okay, that's true. K less than 210. That has to be true. K has to be less than 210. Otherwise, this is going to be negative and the system is going to be unstable. But there might be other additional conditions imposed on this. So that is what we are looking for. Okay, if K is less than 210, this is satisfied. But there might be some additional condition that we might need to impose on this because of this s to the power 1 term here. Okay, so K plus 24, 210 minus K, and that's going to be minus 81k divided by 210 minus k. Just I am telling you, please do your calculation yourself. Please do not rely on me. And okay, we are out of pages. All right, let's do the simplification and see what we end up with. That's going to be 210 minus k, and this is becoming, let's write it down, this is becoming 210k. You're seeing me doing it. K square, 210k minus k square, 210 times yes, 9k is the problem, right? So this is not the only condition that should be imposed, right? If I just impose this condition, okay, you'll see. Let's see. Let's do the calculation. 24 times 210. Bring out the calculator once again. I really should have brought up Python and asked Python to do it for me. But the thing is, back then people didn't have computers, let alone didn't have calculators, let alone computers, right? So again, all these calculations could be done by hand. That's the important point here. Okay, I could always multiply 210 and 24 by hand manually, right? But I'm not going to do that here. I'm becoming lazy and using a computer. 210 times 24, what do I have? That's 5040. 210 times 24, that's 5040. 5040 and minus 24k. So we're just writing this term. Okay, writing this term. So that's what we have. And then we have minus 81k, right? See, let's see. That's 210k. I don't want to mess it up. Minus k square plus 21 times 24. Sorry, 210 times 24. 210 times 24. That's 5040 minus 24k minus 81k. So that's gonna give me minus k square. Okay, and so that's gonna give me minus k square, and that's done. What about the k terms? We have 210 minus 24 minus 81. So we have 210 minus 24 minus 81. That's going to be 105. That's going to be plus 105 k. Okay, happily the constant term is only there. Just 5040. Please confirm that this is correct. Please confirm that this is correct. Unless you do, I cannot proceed, unfortunately. Okay, so this is our rough calculation really. Please do the calculation yourself without looking at my calculation, and confirm that this is correct. If not, tell me the correction. Okay, so we know that this has to be true, and from there we have to, so let's get rid of this entire term. So if you can confirm, please. Okay. Okay, so okay, so you people have confirmed that this is correct, right? So I'm getting rid of this. I'm getting rid of this, and I'm bringing this term back here. All right, all right. Now this has to be positive, right? So we have made sure 1 is positive, 9 is positive. By assuming k to be less than 210, we ensure that this is positive. Of course, k is greater than 0, so this is also positive. So we have to now ensure that this is positive, right? Right? That's rough calculation, right? So now we have to also ensure. Now we have to also ensure that that term is positive. That this is positive. Now something interesting, something important, just you need to recall. Okay, so if a greater than b, then minus a is less than minus b. You know that, right? All right, that's something you know. Okay, also if a is greater than b, none of them are 0 here. Okay, then here 1 by a is less than 1 by b. So if I do a reciprocal, then also the direction of the greater or less actually changes. You already know that. So if it's less than this, then putting a minus sign would change the direction, right? Right. So also say this is a by 3 is greater than, say for example, b, then a greater than 3b. That's true. Okay, that is also true. Okay. Uh, okay. Okay. Also, if say a by minus 3 is greater than b, then a is less than minus 3b. Okay, you can just verify this by putting certain values here. Okay, so these are the certain things about inequality you need to remember. Okay, all right, these are something you need to remember about inequalities that we're going to use here. Essentially, whenever there is a reciprocation or exchange of minus sign on both sides, the direction of the inequality changes. Essentially, the greater than becomes less than, or less than becomes greater than. Same for greater than, equal to, or less than equal to. You have studied this in your school, right? So I am not going to go deeper into this, because inequality is a topic of its own. Inequalities are, so again we are discussing inequalities. You might have thought when you studied inequalities when you in your school that why are you going to use this. This is an example where you actually are going to use inequalities. This is again kind of a rough work. Okay, information. All right, so now this is like a divided by 3, that quantity. So something divided by a positive quantity. So I can bring this to the right hand side and the sign won't change, right? Something like this. So if I say a divided by 3 is greater than 0, then a has to be greater than 0. But if we had a divided by minus 3 greater than 0, then a must be less than 0. Something like that. But since we have ensured that the denominator's term is positive, okay, so we are saying since we have ensured that the denominator's term is positive, or someone have already got the answer. Fantastic. If your answer is correct, then it's fantastic. Okay, so we have already ensured that 210 minus k is greater than 0, right? So it's a positive quantity. So kind of this borderline actually falls under this category, right? So falls under this category. So given that, we can now say that the numerator has to be positive, right? So very simple. This entire thing, this quotient is positive. So, and we also know that the denominator is positive. So if the denominator is positive, then the numerator will also have to be positive, right? In order for the quotient to be positive. So we are saying that this implies k square plus 105k plus 5040 has to be positive. We have to write, since 210 minus k is positive, and why is this one positive? Because we already assumed this condition, we already imposed this condition. So this is in addition to this condition, alongside this condition. Okay, in addition to this condition, since we already have imposed this condition, this has to be true. So the denominator is positive for this quotient, so the numerator will also have to be positive in order for the quotient to be positive, right? Now we can exchange a minus sign from the both side, so you can multiply both sides with a minus sign essentially. So we are going to get k square minus 105k minus 5040, and that's going to be less than 0, because we just exchanged a minus sign, simply because if minus a is greater than 0, then a has to be less than 0, right? Obvious mathematics here, right? Okay, here b is 0 anyway, doesn't matter, right? So now we are thinking about this term. Now unfortunately we have to do a factorization. Okay, we have to do a factorization. Now what is 5040, what is the factorization of that? You can always use a calculator and solve for it, but I am not going to do that. Okay, I'm going to look into the calculation that we did earlier. All right, 5040, that was 210 times 24. Yes, some of you already have greater knowledge of this inequalities, but it's a quadratic inequality here. Okay, it's a quadratic inequality. Now there are plenty of ways in which you can think about quadratic inequalities, but the easiest way is to simply factorize this quantity, right? Simply factorize this. Of course, we know that there are going to be two, it's going to have two factors, right? But right off the top of my head, I don't really know the factors, right? And I'm not going to think about this in terms of what we studied in our schools, right? But can we really? Let's see. I don't think so. That's going to be 24 times 210. It's going to be 12. I'm not sure entirely. That's going to be 48 times 5. 10 times. That's not going to be it. Okay, let me figure this out. Okay, let me see a factorization of this. All right. So what we have to do, apply the quadratic formula, right? So for this k, if this is equal to 0, then k has to be something like minus b, so that's going to be 105 plus minus root over b square minus 4ac. Yes, b square minus 4ac, so that's going to be 105 square minus 4ac, so that's going to be plus 4 times 5040 divided by 2a, that's going to be 2. So these are going to be the two roots, and we can just write k minus one root and k minus another root, and less than this one, right? So 105. See, I could have just asked you to calculate this for me, but I didn't, because I want kind of an independent verification here. b plus minus b square minus 4. So let's do the calculation, right? Let's do plus minus. Okay, let's figure out what that term is. Again, I could have very easily used a computer program to do this for me. Okay, but I'm not, so that you can see my struggle here. Okay, so we're calculating square root of 105 square plus 4 times 5040. I'm really hoping that, oh my bad, so it's a really bad looking term. Okay, let's truncate this to 176.6, let's say. Okay, 176.6. So we're gonna have 105 plus that. Okay, that's gonna be 281. Okay, so this is gonna be 281 divided by 2, or bring up the calculator. Again, this is my collected. This is essentially the problems that I created long ago, right? Part of it you already got. Okay, part of this is you are still about to get. Okay, again, I am collecting all the problems from here. So collection of collections. All right, that's one of the solutions. Okay, and the other one is going to be 105 minus that thing. That's going to be minus 71.6, minus 71.6 by 2. And so that's, instead of saying this or, it has to be and. So 81. Sorry, what did I say? 281.6, right? All right. That's 140.8. That's 140.8, and minus 71.6. That's 35.8. Yes, 5.8. Nice. Nice. So I think these are the roots, right? So this can be written as minus k minus 140.8, 140.8, and times k plus 35.8. That has to be less than 0. So this product has to be negative. Okay, no. So someone is saying, why and? Why am I adding and here? So how many roots does a quadratic polynomial have? 2, right? So the roots are this and this. This and this. These are both the solutions. These are both the solutions, right? That's why I'm writing and. Okay. Now let's figure this out. Let's figure the rest of the story out. This is again a rough calculation, which I do not need. Again, if you have a calculator, then you would have a provision of solving polynomials in a calculator, right? Second order polynomials in a calculator. You can just employ your calculator to solve this for you. Okay. Now this has to be less than 0. Okay. Now, of course, there are plenty of ways in which you can handle a polynomial, a quadratic inequality. It's a quadratic inequality, right? Now this is negative. Now try to understand. This is one number. This is another number. The product of two numbers is negative. Then one of them has to be negative, other one has to be positive. If both of them are negative, then the product is positive. If both of them are positive, then also the product is positive. Right? If both of them are negative, then the product is positive. Okay? And did I make any mistake in the calculation? Okay, what are the roots again? Once again. All right, no problem. Right. So again, one of them has to be negative, one of them has to be positive. Otherwise, this is not going to work, right? If both of them are negative, it's not going to work. If both of them are positive, it's not going to work, right? Right. So now think about these conditions. If I say k is less than minus 35.8, if k is less than minus 35.8, then what happens? This becomes negative. This also becomes negative. If k is less than minus 35.8, then this is negative. This is also negative. So the product is positive. Okay. Now if k is greater than, so now if k is greater than minus 35.8 but less than 140, 140.8, if k is less than 140.8, then we have this term that is negative. So that's this term is positive. Okay, if k is greater than minus 35.8, this term is going to be positive. This term is going to be positive, but this is going to be negative, right? So we have that situation where one of the term is positive, one of the term is negative, so the product is negative, right? Apart from that, so this is a correct one, right? So if now k is greater than 140.8, okay, if k is greater than 140.8, then this is positive, this is also positive, product is positive. That's not a valid answer then. So from this we get this condition, right? So we get this condition, right? So now this condition must be there in addition to, so this is true, in addition to k greater than 0. See, we imposed k greater than 0, otherwise this term is going to become negative. We imposed k greater than 0, otherwise okay, we imposed k greater than 0, otherwise this term is going to be negative, right? And that was the original supposition here. Okay, in addition to k greater than 0, and we also imposed a condition k less than 210, right? We also imposed a condition k less than 210. So all these three conditions must be satisfied. So k has to be less than 210 for this to be true, k has to be greater than 0 for this to be positive, okay, and this has to satisfy this condition for this term to be positive. So essentially, in order for all these terms to be positive, all these three conditions must be satisfied all at the same time, right? All these conditions must be satisfied all at the same time. Thus, we have to figure out a condition that actually would satisfy all these conditions all at the same time. Thus, k will have to be less than, so k will have to be greater than 0. If k is not greater than 0, then see, if k is greater than 0, this condition is satisfied, this condition is satisfied, and also this condition is satisfied, and k will have to be bounded above by 140.8. If this is the value of k, then all the conditions have been satisfied. Thus, therefore, for stability, k must be greater than 0 and less than 140.8. 140.8. Yes, since we got k less than 140.8, k is still less than 210, so that condition is still valid, right? This condition is still valid. We imposed a condition k to be less than 210. That condition is still valid, but keep in mind about this and, okay, in addition to this will also we have to be satisfied, all the additional conditions, right? Yeah. So this is the final condition for stability. This is the final condition, right? Got it? Right. So of course we can understand the system will become unstable if this is going to be if this is greater than 140, right? The system becomes unstable if this is greater than 140. Now let's talk about the instability here. Okay, we do not really need to talk about instability, but let's talk about it. Okay, now if k is greater than 140.8 and less than 210, right? Try to understand. Okay, if k is greater than 140.8 and less than 210, let's bring that, let's talk about this. So now we are saying that k is less than 210 but greater than 140.8. So if k is greater than 140.8, then this is becoming negative. If k is greater than 140.8, this is becoming negative. Okay, but since we have assumed k to be less than 210, this is going to be positive. So positive to positive, positive to positive, positive to negative, and negative to positive. Two sign changes. Two sign changes, right? So if this is so, then we see two sign changes. Two sign changes. So two poles on the right half plane and two on the left half plane. The remaining two on the left half plane, right? Because it's the fourth order system. Now this is one instability, right? So unstable implies unstable. There could be another way the system becomes unstable. There could be another way the system becomes unstable. Okay. Now that's fine, right? All right. There could be another way the system becomes unstable. Right? Say, consider this condition. Say K is greater than 210. If K is greater than 210, now see. Okay, if K is greater than 210, then this condition is violated. So this is negative. This is also negative. This has already been negative. So we have positive to positive, positive to negative, negative to negative, negative to positive. So we once again have two sign changes. Two sign changes, right? So positive to positive, positive to negative, negative to negative, and negative to positive. So two sign changes. All right. So once again, there will be two sign changes. So essentially the same conclusion. Two poles on the right half plane, two on the left half plane. That's also instability. That's also unstable. Okay. Now now there is one interesting thing here. If K is equal to 210, if K is equal to 210, try to now understand. If K is equal to 210, this is not denoting marginal stability, because if K is equal to 210, this is going to become 0, but this is not going to become 0, right? So we won't have an entire row of zeros. If K becomes 210, we won't have an entire row of zeros. So it's going to become difficulty 1, and difficulty 1 ensures instability. Okay, so if I put K equal to 210, okay, this becomes 0 and then becomes 210 0. So this is not an entire row of 0, only the first element is 0 for our purpose, right? So that's the difficulty 1, and difficulty 1 ensures a 0, right? So from that, obviously from that understanding we can make this greater than equal to. Okay, from that understanding we can make this greater than equal to, right? So there will still be two poles on the right half plane, two on the left half plane. So essentially we can combine these two conditions and say if K is greater than 140.8, okay, the system would be unstable, just like that. Unstable. So two poles on the left half plane and two on the right half plane, right? All right, now think about the marginal stability condition. Okay, so of course it will encounter a marginal stability if K is equal to 140.8. Okay, someone is saying, what is the meaning of saying not stable? Okay, whenever I'm saying not stable, I'm not saying it is unstable. It could be unstable. Okay, but not stable means not stable. There could be something else, and that something else is marginally stable. Neither stable nor unstable. Okay, a sustained oscillation. Poles on the j omega axis indicates sustained oscillation if there are no poles on the right half plane. Okay, if there are poles on the j omega axis and the rest of the poles are on the left half plane, then the system is not entirely stable but marginally stable, on the brink of instability, right? Now if K is equal to 140.8, for that purpose let's bring this entire thing to the other side, right? Let's bring this. Let's copy and paste this. if k is 140.8, I'm not really interested about the rest of these terms. Okay, but the thing is, I have to understand. Okay, I have, so again just one more term, so s to the power 1 has to be k. Okay, if k is 140.8, try to understand that if k is 140.8, this is equal to 0, right? Because 140.8 is one of the roots of this equation, right? So that's a 0, right? And 140.8 will actually give me, so this is going to be 140.8, and that's going to give me 210 minus 1. Again, let's bring out calculator. So 210 minus 140.8 divided by 9, divided by happy 9. Nice. So it's like 7.7. All right, that's gonna be 7.7. Okay, oh sorry, yeah, I made a mistake here. Typo, or rather, writing mistake, right? Okay, so that's the situation here. Again, this is going to be a difficulty 2. This row is indicating a difficulty 2. Okay, so this row has to be discarded. This row will have to be discarded. Okay, that's going to be a difficulty 2. Difficulty 2. This row has to be discarded, and this will have to be brought to a new row, s to the power 1, new s to the power 1 row. Okay, and this is going to construct, this is going to be the auxiliary polynomial, and if this is the auxiliary polynomial, so we have aux poly as 7.7 s square plus 140.8 plus 140.8. Okay, that's the auxiliary polynomial, and differentiating this would actually give me 15.4. That's going to be 15.4 and a 0, right? So again, I don't see any sign changes. So positive to positive, positive to positive, uh, positive to positive, and positive to positive, right? So all the poles would be on the left half plane apart from these two, which are on the geometric axis. So auxiliary polynomial. So there will be a complex conjugate pole pair. So two poles, pole pair on the j omega axis at s equal to plus minus j 140.8 by 7.7 and square root of that. So that's gonna be s equal to plus minus j 140.8 divided by 7.7. Let's divide 140.8. 140.8. 140.8. Wow. That's gonna be 18.3. 18.3. That's gonna be and of course I have to take a square root of that. Take a square root of that. That's 4.28 minus 4.2. Okay, so there will be a complex conjugate pole pair on the j omega axis. So since I do not see any sign changes here, do not see any sign changes, so the rest of the poles are going to be on the left half plane, right? So we can say, therefore, if k is equal to 140.8, there will be two poles on the j omega axis which are at plus minus j 4.28, and since there are no sign changes on the route table, since there are no sign changes on the route table, there will be no pole on the right half plane, thus the remaining two poles will be on the left half plane, which indicates marginally stable. Yeah, we did take the derivative of 7.7 s square. Okay, you made a mistake. Yeah, we did take the derivative of 7.7 s square, and we put that. We took the derivative of 7.7 square. And why do you think we got the term 15.4? Why did you think we got the term 15.4, right? Right. So we finally figured out that the system would be stable if this condition is satisfied. Otherwise, the system is unstable, and out of that, otherwise the system is not stable. And out of that, if k is equal to 140.8, then the system is marginally stable. So there will be two poles on the geometric axis, and the rest two would be on the left half plane. So that's the end of today's class. Thank you for being patiently here. And if you have any query, just feel free to ask. And otherwise, we are going to end our discussion at this point. Really, thank you very much. So I think this idea was clear, right? There was nothing very difficult to grasp here. If you have any query, just ask. Otherwise, we're going to end this discussion here, and I will see you next week. Okay, someone is saying, why don't we consider k less than 0 to be unstable? Yes, if I have k less than 0, then the system becomes unstable. But it becomes unstable due to another reason, not the way you would think. Okay, of course, having k less than 0 would result into unstable systems. Okay, but that's why we have this condition imposed already, right? We have this condition imposed for stability. We are specifically mentioning that k is greater than 0, right? But then again, k less than 0 would make the system perpetually unstable. But that is something we do not discuss in this course here, because that would make the system unstable in a slightly different fashion. Okay, not the way you would think. Of course, the poles are going to be negative, but that's a completely different thing, and that is kind of an advanced topic when k is negative. Okay, the values of k when it is negative, it is actually taught as an advanced topic in the chapter of root locus. So if you go through the book by Ogata or some other books on control system, you would find some discussion on negative values of k. What is root locus? We're going to discuss that later on. So kind of an advanced version of this. Okay, and there you would see that for negative values of k, that's a very interesting situation. Okay, negative values of k. So we call that negative amplification or negative gain. Okay, so at least for our course here, the preliminary course on control system engineering, we do not consider negative values of k. But yes, we do have certain particular uses of negative values of k, but we kind of don't use that here. But for rest assured, negative values of k would make the system unstable, but we do not discuss that here. And we can also just figure out how many poles are going to be on the left half plane, right half plane. Just to tell you, if k is negative, if k is negative in this particular scenario, okay, see we have a positive number here, positive to positive, positive to positive, and again this is going to be now if k is negative, what condition did I impose on this? If k is negative but not beyond this, then this is going to be positive. Otherwise, if k is beyond this, then this is going to be negative, right? So in either case, we would have one pole on the right half plane. One pole on the right half plane. If k is negative, in either case, we would have one pole on the right half plane. Okay, unlike two poles on the right half plane. Okay? Something fishy is going to happen. Okay, what would happen to the j omega poles? So there are certain interesting things that would happen. But again, we do not discuss negative gains because we seldom encounter negative gains. All right, and when we encounter negative gains, that's an advanced situation. We do not really see those kind of things. But sometimes we do. In particular controller designs, we would encounter negative gains. But again, that's a particularly advanced topic. We will not discuss. Right? But nonetheless, using this tool, you can think about the negative gains. Okay? You can impose those conditions. You can figure those out. The Routh-Hurwitz theorem and Routh-Hurwitz criteria won't break down for negative gains. No, not at all. Alright, any more questions? If you don't have any more questions, so that will be end of today's discussion. Thank you very, very much. And I will see you next week.